Hey there guys, so figured I might as well go ahead and make a series of physics videos because I'm a physics major, although I guess I'm not entirely sure why I'm doing it because I'm not Asian and my name is not Sal, which means that I really don't have that much going for me. But yeah, so just start from square one I guess, which is a little bit of mathematical background in the form of vectors and scalars. So let's look at what a vector is really quick. And so what a vector is, it's going to be a geometric entity that has both a magnitude and a direction. So it's going to be something that looks like that. And the way you can think about this, or you can visualize this, is by picturing something, say like a box or a car or anything that you want, and we're going to take it and we're going to move it, and we're going to move it in a particular direction. So we're not just going to move it 5 units, we're going to move it 5 units to the right. Sound familiar? Maybe you've been watching Khan Academy. But he's correct. This is what a vector is. Take it and move it 5 units to the right, as opposed to a scalar, which would be something along the lines of taking a box and moving it 5 units, but not specifying a certain direction. So what this means practically, as far as, like I said, a geometrical interpretation, is that a vector is going to be something like this. It's going to have a magnitude and a direction, so we'll have our x-axis here and our y-axis here, and we're going to be moving, as you can see in this particular one, we're going to be moving up from the origin up and to the right. And so what that means is this could be something like a vector that is, I don't know, say 3, 3. And generally, if you have a vector, you're actually going to write it with a little less than bracket there, like this, and then you'll have your inputs, and then you'll close the bracket like that. And so what this means is this first one here, this one is going to be our x input, or our x1. You might actually end up seeing something like, it might not be x and y, it might be an x1 axis and an x2 axis. Sorry for that color difference there. So this will be our x1 and this will be our x2, where we are then specifying basically the direction and the magnitude that we're going in that direction with that input. And as you can see, if we were to have a scalar, then that might just be something like 6 or 5 or 10 or any number. It doesn't have to be an integer. It could be a negative number. It could be negative 6/12. I guess that would just be negative 1/2. But yeah, so what you'll see then is I'm going to go ahead and clear this as a general representation. We'll have a vector, we'll call that v, and you denote that it's a vector by putting a little hat. You might also see it denoted as a line instead of a hat, or sometimes, depending, it might be a unit vector, which we can talk about later. It might have a little hat like that, or you'll see something along the top or the bottom that will indicate that it's a vector. And yeah, and so what this is going to be is, like I said, it's going to be an x1 value and an x2 value. And you could have actually more than that. You could go all the way up to however many x value, or however many different like planes you want, which is a little bit hard to visualize, I suppose, because then you would move out of like a 2 or 3 dimensional thing. But you could, in theory, you could have something, a vector that was an x1, an x2, x3, all the way up to xn. So like I said, that's a little bit harder to give a geometric interpretation of, but again, that's just going to be specifying the magnitude and the direction of it. And so let's talk a little bit about what this magnitude and direction mean, I guess. So, the magnitude, that's just going to be the length of a line. So, we could have our v coming like this, and that's going to have one magnitude. But then let's say if we had it come up like this, then it's clearly it's going to have a larger magnitude. And then as far as direction goes, well, what that's talking about is like this angle here, this angle up from the edge. So basically, what direction it's pointing in, which way you're going, whether that box that we were talking about earlier is going to the left or the right. And yeah, so that's what a vector is going to be. And then a scalar, on the other hand, we'll just call our scalar alpha. You might see it called any letter, any Greek letter, any number of things. And that, like I said, is just going to be a number. So that's going to be any number. So, like it could be 1, 2, 2, or 3, I guess, 0.6, 7, 9, 1, etc., etc. And one thing you may notice now is, let's say we have a scalar here, our scalar alpha, and we want to multiply it by our vector v. Well, what is this going to entail? And as it turns out, we'll actually just do that component-wise. And so what that means is that instead of having, as we had before, we had let's just go ahead and write them out, and then let's just make it a x1 and x2. We'll leave out the rest of them, but you could obviously extend this. And so what this means is that we're going to do it component-wise. So we're going to take this alpha right here, and we're going to multiply it first by x1 and then by x2. And if you think about it, this makes perfect sense from the rules of multiplication, and I think it would be the distributive property that you probably learned in elementary school. And so what this is going to look like is we're going to take it and we're going to have our alpha v. Let's just rewrite this real quick, and that's going to equal, go ahead and keep the color scheme consistent, alpha times x1, and then we're going to have alpha times x2. And so you may notice that we're actually going to get out a vector if we put in a vector. And so this is going to be, we could call this any other letter. So we could call this our vector A. So we're going to get some other vector out. Yeah, and you can also, from here pretty easily notice that if you multiply two scalars, so if you multiply an alpha and say a beta, then you're going to get another scalar. So say kappa, you're going to get a scalar. Whereas if you multiply a scalar times a vector, then you're going to get a vector back. So yeah, let's do this real quick. Maybe a more concrete example, just very briefly here. So let's say we have a vector, and we're going to call this vector vector v again, and this vector is going to consist of 2, so 2 here, and 3. Alright, and this could be any x1, x2, but we're just going to go ahead and pick 2 and 3, and so let's call our scalar alpha. Let's say we want to take this vector and we want to double its length. So instead of having this vector like this, we're going to have it come all the way out here, and it's going to have, its length is going to be double what it was before. And so alpha here then is going to equal 2. We're just taking it and multiplying it by a factor of 2. So in other words, we have alpha v, and that's going to equal, doing it component-wise as we did before, we're going to have this 2 here times this 2 here for that first slot. So we're going to get a 4 for that first slot, 4, and for that second slot, we're going to multiply it by this 3 here, and so then we're going to get a 6 for that second slot. and oops, make that black. And if you wanted to plot this, well, you can see it's going to go up. Here's our 2, so it's going to go up to 4. And if this was our 3, it's going to go up to 6. So it's going to look something like this, which, as you can see, it has the exact same direction as the original vector, but it has a different magnitude. So I suppose that's another thing that you can notice when you multiply by a scalar. It does not change the direction of your input vector. It's only going to change the magnitude. And yeah, and then we can look at, next time, we'll look at something called a dot product, which is what's going to happen when you take a vector, call it v1, and you multiply it, see if I can get a multiplication symbol there, by another vector. So you can go ahead and think about that and wonder maybe what you think we'll get out. Maybe we'll get a scalar, maybe we'll get a vector out. But there's a definition of how to do this, and this is called the dot product, actually. And it's very useful in physics and other disciplines as well. Has a lot of applications, and so yeah, definitely check back next time. All right, take care, guys. Goodbye.